Yeah, let us move on to the next topic. So when this far field approximation is valid, okay? So let me write down the exact form, which was like this integral. And the far field um, with approximation is gonna be 4 pi r mu exponential my j beta. And so in order for us to arrive at the the bottom equation from the top, what we have assumed is 2. Actually, the denominator was approximated by 1 over r, and this is one assumption. The other assumption is that actually the exponential minus j beta minus r dash was approximated by j beta r plus beta dot r dash. Okay, so we're going to focus on like the second assumption. The To do this, let's look at this term. The absolute value of this r minus r dash squared. We can rewrite this one as like an inner product between, inner product of uh, r minus r dash. It's gonna be r squared 2 r dash plus r squared. Okay. Then we can factor out r squared terms, so 2r. Now we can take the square root of it, then r over okay. So let's take this whole thing as an x, and then this one is r1 plus x. We can use this Taylor series, so that it's gonna be 1 plus 1 over 2 x minus 1 over 8 x squared blah blah blah. We can explicitly rewrite this so that what we have is r minus r hat r dash. By the way, r is the r hat times r. Okay, r hat is unit vector, and plus 1 over 2 and r dash square, and r is 1 over 2 r hat dash r dash squared r. So actually, it turns out that if we take the first two terms from this for the absolute value of this displacement vector, then it's gonna be the far field approximation for the phase vector. Okay, so we can ignore the higher order term as long as um, Actually, the order of these terms is going to be r dash square or r, and also um, r hat dot r dash is always less than r dash, so it is also of the order r dash squared r, so that if we multiply the beta this order, and if this order is gonna be far less than unity, so that we can ignore this higher order term, okay, so that we can recover the far field approximation. So again, if this condition is ensured, then we can use uh, far field approximation. Um, and then let's talk about these three zones: near, Fresnel, and far zones. If we have antenna will radiate field. So we can actually the radiated field. Um, I mean the characteristic of EM field varies depending on the distance between this antenna. So we can broadly divide the region into two. I mean the near field and the far field. Of course, in a far field, we know that the radiated field can be approximated by spherical wave, the wavefront. And if you look at this spherical wave locally, then it's almost like a plane wave. Okay, what is the property of plane wave is that electric field is perpendicular to the magnetic field, and also they should be perpendicular to the uh, propagation direction. And near field can be further divided by two regions. One is that reactive near field. The other one is the radiative near field. It is also called the Fresnel region. Actually, the reactive near field is the region where the fields are almost non-radiated, but they are reactive, so that the energy is transferred back and forth between the source and the near field. So this is the reactive energy. In the radiated near zone or Fresnel zone, actually field starting radiating. However, it is not completely a spherical wave, but it's kind of transition between this near field and far field. So fields are um, still significantly vary with the distance. So it's kind of intermediate zone between non-radiated and radiated far field zone. Um, Actually, yeah, this is the um, this is a kind of a boundary between. This is a distance boundary between the near and the Fresnel zone, and this is the Fresnel zone and the far field. Okay, this distance is called the Rayleigh distance. Actually, out of time. So let me just briefly describe this Rayleigh distance. So in a near field, we have non-radiated field, but intermediate region, which is the Fresnel region, the field look like, I mean, if the aperture radiate a field, EM field, this is the aperture, Gaussian, and it'll take like a Gaussian beam in the Fresnel zone. in a far field, you know, they take the form spherical wave. Okay, the Rayleigh distance is between the boundary between this Fresnel zone and far field zone. So actually, the detailed mathematical derivation for this is displayed in lecture notes, so you can refer the lecture note. So this is all that I prepared. Are there any questions? Yeah, look, very complicated mathematical things, but again, the key idea is that if we make Hertz dipole antennas in an array, uh, this kind of factor appears so that we can achieve the high directivity. That's the key thing. And depending on the design parameter, like D and linear phasor, we can make broadside antenna or end fire antenna. And we have inspected like a condition when far field approximation is valid. And also we have discussed about near Fresnel and far zones and characteristics of radiated, I mean, um, field created by antenna in each zone. Okay, so we can stop here. So thank you for joining today.